Yeah, so thanks a lot for these kind words as the introduction, Martin. And yeah, welcome everyone. It seems like we lost some people due to G-data yesterday evening. But nevertheless, it's good to see that at least some people made it here this morning. And I want to start the presentation with some kind of advertisement. Because as you probably know, IT security is a very hot topic at this point, and there's actually quite a lot of interest also in the industry about the different solutions, how to prevent the attacks, what we can do about it. And therefore we decided to do something, so basically to provide some incentive to you to think about whether it makes sense to start a company. As you probably also know, there are a lot of computer security companies around, many startups that evolved in the last few years. And what we want to do is also basically provide some kind of culture of startups in Europe. And for this we started this Security Rockstars competition. We have some prizes, so the main prize is even 20,000 euros, so that you have some kind of incentive to also apply. And it will be co-located with ACM CCS in October in Vienna, in the Hofburg. You can find more information on the website, and Yvonne is around here. So if you have questions about the competition, just talk to her. She will probably provide you with all the information you need. And in my talk, I want to talk about code reuse attacks, control flow integrity, so both attacks and defenses, and also rumble a bit about what we've done in the last few years and what I think will be the main challenges in the future. So what can we expect in the, let's say, next 5 to 10 years? How will this kind of arms race, as Martin also said, evolve in the next few years? But let me start with a look back. So where is all of this coming from? Probably you've all seen this picture. It's von Neumann in front of an ENIAC. And actually, many of the problems that we face today are due to this kind of computer architecture. So the von Neumann architecture, where we have one memory space, and in the memory space we have code and data interleaved. So actually during runtime, it's only decided whether a specific memory location is interpreted as code or if it's interpreted as data. And this is actually one of the fundamental reasons why we have all of these buffer overflows and the other kinds of attacks that we see today. Because an attacker can inject his own code into a vulnerable process. This code is then first interpreted as data, because it's data that the program is processing, and then later on, once the vulnerability is triggered, this data turns into code that is then executed by the processor. So von Neumann actually is responsible for many of the jobs that we have in today's industry. But actually it's also not only his fault, because there were also, even back in the 50s, 60s, many computer architectures that already had security in mind, that had a clear separation between code and data. One example is here the Burroughs 5000 or the 5500. Also one of the computer architectures developed in the 60s, 70s. So this is a picture from 1964. It's a Burroughs 5500. And the interesting thing is that in this kind of computer, they, as I said, took security already in mind. They had a clear separation between code and data. And even in today's terms, they had some innovative features. So they had some kind of what they called executable space protection. And the capability was that there was a tagged architecture. So each memory location had basically a tag, such that it was decided whether this is code or whether it is data. And data cannot be executed, and code can only be executed. So they had a tagged architecture that also some of the modern processor architectures have. And unfortunately, Intel and others don't have it, so we need to emulate all of this in software. Also, some of the other concepts that we recently worked on in the academic field, like execute-only memory, such that you have one memory page that it can only be executed, but it's not readable. These are concepts that are actually, or that were developed a long time ago, that we had all the access bits and everything. But somehow it seems like we forgot about all of these features that were developed back then. So we are actually rediscovering quite a lot of the things that were already available in the past. I think another milestone of the modern attacks is this study published in 1972. It was an Air Force study where Anderson reasoned about potential attacks against computing systems. And this document, as I said, from 1972, already described buffer overflows, such that basically if a memory location has a fixed width, that an attacker can write past the boundary and then potentially also access control structures. So he already described the concept of buffer overflows back in 1972. So it seems like many people, or at least some people, already knew about it. And then probably the event where most of the things came to a larger audience were in 1988 with the Morris worm. Here's just a code snippet from the worm where you see that it's basically preparing some kind of shellcode. So a buffer is filled and then the buffer is also adjusted a bit such that it represents the actual stack layout that is needed in order to take control. So that's one of the first publicly documented examples of buffer overflows, and so basically the grandfather of what we know as buffer overflows today. And then I think the golden time of Frag and Bugtrack and all of these magazines and websites emerged. So there we've seen lots of innovations. So actually many people developed new techniques in order to take control over vulnerabilities. So concepts like return to libc were developed back then, all the format strings. Many also heap-based exploitation techniques were developed. So these were actually 10, 15, 20 years in which lots of innovations happened, especially on the attack side. So Frag and all those magazines documented quite a few neat tricks that, or many of them even apply today, or have at least inspired many of the attack techniques that we even see today. As a response, of course, also on the defense side, many things happened. Here are probably the two examples that are most widely deployed in the wild. On the one hand, we have data execution prevention, so the idea that a memory page can be either writable or executable. And when you try to interpret data as code, the processor stops you. So the first implementations were just based on a software emulation, but nowadays this is available in the processor itself. So the overhead is quite low, and almost all devices, from desktop to even those smartphones, typically have data execution prevention implemented by now. And the other widely deployed thing is address space layout randomization. So the idea that we try to cope with the monoculture, that each process has the same memory layout. So the easiest way to do this is just to re-randomize the base address of libraries, such that when you start a program twice or after a reboot, the memory layout looks different. And this is also one of the concepts that's quite prevalent. And especially in the academic literature, many new techniques have been developed for more fine-grained address space layout randomization, where you do not only randomize the base address, but also, for example, within a library, you can do re-randomization. You can insert some things like just NOP codes in order to just change the structure a bit. You can reorder code in order to also somehow distort the memory layout. All of these more fine-grained techniques didn't adopt widely yet, so I think there are no major systems that already have fine-grained randomization, but still I think this is one of the interesting challenges for the future, how to basically implement address space layout randomization in a scalable way such that the overhead also is rather low. And all of these techniques with software diversity, so where you try to break the monoculture by providing individual binaries of an executable to all the different computers, are promising ways, but also quite a lot of problems still need to be solved related to patching, related to updates, related to also development or debugging. So I think there are also as challenges, but probably an interesting area to take a closer look at. And since those two techniques are in place nowadays, also the attack side had to advance. And there, I think the main two papers in this field were, on the one hand, a paper by Stealth or Sebastian Kramer on the borrowed chunk or borrowed code chunk exploitation technique, and from Sasham on return into libc without function calls that introduced the idea of return-oriented programming. Both papers were published about 10 years ago, so Sebastian's paper 2005, Sasham 2007, and in those last 10 years these techniques were refined quite a lot. The basic idea is still the same. So the idea is that instead of injecting code as an attacker, you can just reuse existing code, because each program has many pages that are executable, so that represent the text section of the program that has or that is loaded in memory, that has certain vulnerabilities. And then the idea is to reuse the code that's already available, so that you do not need to inject your own code as an attacker, but you just reuse what's already there, because it's may be protected via some kind of signature. It's also executable, so you don't need to mess with page permissions or anything. So you just reuse the code that's available there. Here on the slide you see a small example of how return-oriented programming looks like. So you have different so-called gadgets. Each gadget represents some kind of micro instruction, for example, that you add two values or that you pop values from to the stack. So the idea is to basically chain some of these gadgets, and the gadgets are then executed after each other. And with each gadget, you just do some kind of specific operation to prepare registers, to prepare the stack, or to take values from the stack. And then finally, you do an operation, like you add some values, or you multiply, or you perform a jump, or a memory access, or something like that. So the picture in the lower right basically has a representation of how you can think of return-oriented programming. So you're just chaining small values, and at the end, the reuse code that's already available is doing the computations that you want to do as an attacker. And preventing this kind of attacks is challenging, especially since there were many advances on the offensive side. So here's a slide from Luca, who will have his presentation later on today. He will dive into some of the details. So this is basically a timeline how all of this evolved from return to libc to the new attacks that we see today. And Luca will talk about, let's say, stitching gadgets, jitter, and also a defense. So he will provide more details about the different kinds of attacks in his talk later today. And what we already, or especially see, is that especially real-world exploits also leveraged ROP in order to bypass the defenses. So especially around 2011, or starting from 2010, 2011, there were many publicly documented exploits that took advantage of ROP in order to bypass the defenses. I think the interesting insight is that this trend seems to somehow stop now, because now major operating systems like Windows 10 have control flow guard implemented. So basic defenses against return-oriented programming are adopted by also major operating systems. And I think what will happen is that the practical value of return-oriented programming will diminish over time. But on the attack side, we also saw that many new concepts were developed, and I will talk about a few later on in my talk. So we have this arms race. On the one hand, we have ongoing attacks. So the attacking side is developing novel techniques. They are thinking about how to bypass the existing defenses. And then on the other hand, we have all the different areas how this control flow hijacking or code reuse attacks can be prevented. So we have the typical yin and yang between offensive and the defense side. And this slide just provides a brief overview of some of the defenses that were presented in the last few years. Many of them target either binary or source code approaches, and those were all academic papers that presented concepts. I think Cling is meanwhile adopted by some operating systems, but the others are mainly concepts that didn't receive a widespread adoption yet. Some of them will probably be adopted soon. For example, you have some compiler patches available for both GCC and LLVM that provide control flow integrity to a given binary. So some of these concepts, while only being academic prototypes, will probably be adopted also by mainstream systems in the near future. At least I hope so. So from a broader perspective, you can think of different areas how control flow hijack and code reuse attacks can be prevented. And the different approaches how to tackle the problem basically target different concepts of the actual exploitation attempt. So the first column, the memory safety, is targeting the root cause. Because if we allow the attacker to have something like a write 4, such that he can overwrite 4 bytes of memory, then he can bypass probably most of the defenses, because once he has a read-write primitive, he has, I think it's pretty hard or pretty challenging at least to stop the attacker. So all the memory safety techniques, what they try to do is to prevent the attacker from corrupting data structures, from corrupting memory, especially things like CPI or CPS were discussed quite extensively. They have certain limitations because it's tough to implement this in a precise way in x86. In x64 you try to just hide some secret information. That's also not that easy. And so these systems provide or make it harder for an attacker, but they also cannot provide any guarantees. But then we have techniques like soft bounds or VIT that definitely are harder to bypass, but the drawback is that they are actually rather costly. So soft bounds actually has an overhead of about 100%, so your runtime is suddenly only half as it used to be, and that's probably too much in most use cases, although soft bounds can guarantee you that nothing can go wrong. So it's definitely an interesting approach, but what we need are more efficient ways to do this. So I think that's one of the main challenges. How can we achieve memory safety without or with an acceptable overhead, such that we provide integrity of data structures, provide integrity of the memory state, but still have only an impact of maybe 10 or even less %. The second column, or those control flow integrity approaches, are interesting in the sense that they try to tackle especially the point where the attacker tries to escalate his privileges, so where he tries to execute his own code. The basic idea behind control flow integrity is actually easy. It's been documented since many years, and it works as follows. Given your program, you first determine which states the program can be in. So typically you construct something like a control flow graph where you just represent the different states as blocks, and then you connect the blocks to each other via edges, and each edge represents a valid control flow transition. And what you do then during runtime is to enforce this control flow graph, such that each jump that the program is doing only follows a legitimate jump. This prevents control flow hijacking attacks, because the attacker is prevented from jumping to his own shellcode, and it also prevents, at least to a certain extent, code reuse attacks, because the attacker is heavily restricted in which edges he can take. Control flow integrity is also a concept that's, as I said, widely available in compilers by now, so you can actually use it. It's available in Windows with Control Flow Guard, with Windows 10. So we see more and more widespread adoption, but the challenge here is to have a precise control flow policy. Probably Luca will also talk about a bit about this, because many of the implementations that were presented can be bypassed, either because they have implementation flaws or because the policy was not precise enough that the attacker can still somehow bypass it. And the main challenge also with control flow integrity is that even in a benign binary, you have many functions that you can use, and if an attacker performs whole function reuse, so something like return to libc in a more elaborated way, he can also bypass many of the, or at least some of the proposed systems, because if he reuses a full function, then this looks like a legitimate code path that is followed. The third area are all those randomization techniques that do something like code shuffling or rewriting or try to hide some information. So these basically, or all of these approaches basically are just randomized in the sense that they typically cannot provide any guarantees. They just try to make it harder for an attacker. And I think all of, or most of these have been bypassed. Redactor is probably the state-of-the-art system in that space, or Redactor++ by now, that tries to reduce the attack surface as good as possible. Redactor++ has a certain memory and also a runtime overhead that's probably still acceptable in practice, but Redactor++ can also be bypassed because some of the code pointers are still controllable by an attacker, and so it's even possible to bypass even those state-of-the-art systems. And then the last column are just a collection of systems that just provide some kind of heuristics. So they are just some heuristic in order to estimate whether a given piece of code is actually following legitimate paths or not. K-Bouncer received a lot of attention because it was awarded $200,000 by Microsoft as part of the Blue Hat Prize, but it was also bypassed, I think, 1 or 2 weeks later. So all those heuristics actually turned out to be pretty weak. EMET can be regularly bypassed, Opeka 2. So all of those heuristics have the problem in practice that they are not precise enough. So, and I think attackers always will find bypasses. So it seems like all the academic approaches that were presented and also what's available in commercial systems doesn't provide a lot of hurdle for the attacker. So it makes it harder. Something like ASLR, which is just something that the attacker can bypass if he just provides enough effort. And we cannot provide any guarantees. So the state of the art is unfortunately very sad. Attackers seem to have the advantage. We seem to not be able to somehow contain them, because once they have something like a read-write primitive, once they have something like an information leak, they can always bypass our systems. So it seems like we need to go one step further and try to take the attackers away those primitives. And yeah, the main two challenges here are, on the one hand, information leaks. So when the attacker has the information or about, let's say, a base address or something, he can typically escalate this pretty quickly, such that he then knows more code locations and can then bypass all of the defenses. So, and I think that's one research area we should focus more on, are all the information leaks. So how to find them, how to prevent them. But it turns out that this is actually pretty challenging, because once there is some kind of vulnerability, an attacker can typically turn this vulnerability into an information leak, and typically he can also abuse regular constructs in order to construct then information leaks. So finding them is challenging and probably, or at least my opinion is, probably cannot be fully automated in the end. And the second example are all those read-write primitives. So when an attacker is able to change 4 bytes in memory, or sometimes maybe even 1 byte is enough, or maybe even less, then he can lead typically the program into a state that then either crashes the program, or that escalates its privileges, or even allows code execution. So the combination of an info leak and then a read-write primitive is typically enough. And that's typically the first step. And all of this return-oriented programming or so are then just techniques in order to bypass other defenses. But to prevent the attacks, we need to tackle info leaks and the read-write primitives first. I then want to talk about one paper we did recently on how to at least detect information leaks. It's definitely not perfect. It cannot be easily used in practice, but still, I think it serves as an idea, and probably this can be improved, and hopefully we'll find better ways to do this in the future. To understand what we do, I first need to explain a bit how info leaks work in JavaScript. So we have on the left just a JavaScript object. And what the attacker can then do in order to construct an information leak is he can, for example, override the length field. So the length field is set to 1000 first, and then he just adds 4. So he overrides the length field because he has a read-write primitive, changes this to 1004, and via this change here. So he overrides the length field to 1004, and then the buffer is then a bit longer, 4 bytes longer, and so this v pointer is, or virtual function pointer, is then leaked because it's included in this data structure, and then the attacker can read the virtual function pointer. He knows the value of the function pointer and can then use or start to abuse this virtual function pointer in order to leak more information. So by just overwriting one field, he can disclose information, and this is what I meant earlier. Information leaks typically don't just exist, but the attacker needs to construct them by cleverly overwriting certain structures. A second example is if he can also target the data pointer by just basically changing where this pointer points to. He just moves this a bit up, so to a higher address, and then he can also get access to the virtual function pointer that's available in this JavaScript data structure. So the attacker has quite many ways to abuse his read-write primitive in order to then construct information leaks. But still, the observation, and that's basically the main idea behind what we do, is that an information leak is constructed by the attacker in the JavaScript context. So he abuses some problems in the JavaScript context in order to get a memory pointer into the JavaScript context. And that's something that should never happen, because JavaScript is running on a more abstract level. The JavaScript context should never contain some information about memory locations. And if the JavaScript content has information about the memory layout, then clearly something happened previously. And what we then do is we take the idea of n-variant systems, so that you have here one system and duplicate it, or you have even several duplicates, and those duplicates are then running in lockstep, such that you precisely synchronize the execution of the different processes, and you also compare the state of both processes, and once they start to diverge, then you have detected something. So the idea of this n-variant systems is also pretty old. It has also been done in the 70s. And what we do is we do this on a more precise level, in the sense that we do this in the JavaScript context, and we do this also for binaries. And in our case, we do this for Internet Explorer 10 and IE 11. So the idea is that we do, on the one hand, a per-process re-randomization, such that the memory layout of the two processes is different. So here we have on the left the so-called master process, and then on the right the twin process, and both are re-randomized in the sense that the memory layout on the left is different to the memory layout on the right. We do this by just messing a bit with the loading mechanism, such that we make sure that all libraries are loaded to different addresses. And what we then do is a dual process execution. So we make sure that the master and the twin are executing in lockstep, that they are synchronized in the sense that the state of both processes is also kept the same. So we need to take care, for example, of randomness. So if the master is generating some random data via something like math random or something, we need to make sure that the twin process gets the same randomness. Or if data is received from the outside, that both processes work on exactly the same data. And then once this, the IPC between both processes is set up so that they can be synchronized, we closely observe what's happening in the JavaScript context in the master and what's happening in the JavaScript context of the twin. And then here, once an information leak manifests, then you have an illegal read here from the heap to the JavaScript context on the right. And the same also happens on the left. But since the memory layout of both processes is similar, the leaked addresses are also not the same, and so we can detect that there's not the same state in both processes. So we have one pointer here and a pointer with a different address in the other process. So they diverge, and this is the point where the information leak is actually manifests, and so this is the earliest point possible where we can detect that something is going wrong. We, as I said, implemented this on Windows 8 with Internet Explorer 10 and 11, and the idea is that basically you have a wrapper for the IE main process, and then each time you start to browse, we do this in an automated way that we create a twin, we set up the IPC channel, we closely synchronize what's happening, and also re-randomize the twin. Actually, do this in the first step. As you can imagine, that's quite a lot of implementation effort, because you do this with IE10, with the Chakra engine, so a highly optimized piece of code. You need to dive a lot into details. I think the PhD students probably implemented on this. I think we probably spent more than one person a year just on the implementation. It was a bit of a crazy project, but at the end it works. The overhead is a bit on the higher side, so definitely not something you can easily apply to all of your desktops. So the startup time is about 1.3 times, so it's definitely slower to start up. When you then do browsing, and here we have a small benchmark on some popular sites, there you see that the average overhead is about 17%. So it's not really noticeable, but you can still measure it. And there's a certain overhead. So it's not just 1% overhead, but more like 17%, as I said. So it's still some engineering would be needed to basically bring this down to a more reasonable level. The only advantage is that since the browser is optimized so much that it shows you some rendering as fast as possible, and everything what we do actually is happening in the background, and the user typically doesn't see anything. So it's not really noticeable for the user. We tested this with several pure information leaks that, for example, just leak some information from an image, so some image processing problems, or some other memory location, some other info leaks for different kinds of browser-related vulnerabilities. And of course, we detect it just by design. And when browsing through the Alexa Top 100, we also didn't get any false positive. So the concept works. It has a certain overhead, especially on the memory side. So we have about 50% more memory consumption. So there's also something that needs to be done there. But I still think that that's a viable approach in order to basically try to tackle information leaks. Probably there are better ones. So I think that's something where we need to spend way more time on how to detect, how to prevent information leaks, because that's one of the root causes. If you take a look at modern attacks, one of the first steps that they do is that they use an info leak, and only later on they can bypass all the other defenses or use other techniques. And then in the last 10 minutes, I want to talk a bit about other things we do, or what I think is also the challenging attack side in the future, that we are moving more and more away from from return-oriented programming, but to other kinds of code reuse attacks, and especially code reuse attacks that do not modify code pointers, because I think we better understand now how to protect code pointers. But all those data-only attacks, so where the attacker doesn't modify a code pointer, but where he only modifies data structures in order to influence the control flow, I think that's something that will keep us busy in the next few years, because that's also way harder to protect against. I want to start with just a brief overview of a paper that we did also 2 years ago, where the basic insight is that hooking actually got much harder. So traditionally you would do something if you want to implement a code hook, that you override here a specific code pointer. The code pointer then doesn't point to the legitimate function, but it first points to your hook. In the hook you do your computations that you want to do as an attacker, and only afterwards you call the legitimate function. So you divert the code pointer to your hook. Or if you want to implement a data hook, you basically do something similar. In the syscall table, you override one of the entries. The entry then points to your hooking code, and then only afterwards you basically call the legitimate function. There are many techniques available to provide integrity for this kind of data structures. So code and data hooks are, I think, well understood, and there are, as I said, many defenses already available. And especially those changes of control data that's needed with this kind of hooks is easy to detect in practice. But what's harder to detect is if the attacker abuses legitimate code. So if he performs some kind of data-only attack in order to then implement this hooking mechanism. And this works as follows. So imagine you have a code block that's doing nothing more than just writing a value to a memory location at a specific destination. So we have here a write, and the write can be something just like a move instruction that moves a certain value to a specific memory location. What we then do in the first step is we go backwards in the code to figure out where was value and where was destination written for the first time. So where was it loaded? So we go back in the control flow graph and find specific areas or specific code locations where a load for A happens, where a load for B happens. And then we see, okay, in these code locations we load the values. Then we follow the path downwards again and try to see what kind of computations are happening on A, what kind of computations are happening on B, and how does this influence value and destination at the end. There you can do something like symbolic execution. So basically from here you just go downwards, just collect the different expressions, so the things or computations that are happening on the path. You basically solve those constraints with some tools, and then at the end you know, okay, here at the beginning the initialization happened, there were some computations happening on the path, and at the end basically your system tells you, okay, you need to initialize value to a specific, or you need to initialize A to a specific value such that it has a specific other value at the bottom, and you can also do the same for B. such that you know, okay, how do I need to influence A and B in order to influence the destination and the source. And once you have this, and that, as I said, can be fully automated, you can use this in order to install your hook on demand. And the interesting thing is that this will then only be activated during runtime. And now the question is, where do we find this kind of abusable code locations? And one instance of this would be something like a linked list. So we have just a data structure that has a next and a previous pointer. And what we now do is we want to abuse this kind of data structure to implement the idea that I just explained on the previous slide. And what we do is we create a list entry. And the list entry is created in a specific way, such that we create this list entry as an attacker. We point the next pointer to a specific address where the hooking code that we want to trigger is located, and the previous pointer is located to the stack on a specific address where a return address is located. And what we then do is with this modified list entry that we then trigger, that it should be removed from the linked list. Removing an entry from the linked list is actually two operations. We need to adjust the previous and the next pointer, that's on the top. And on the assembler side, it looks like this, that the next pointer is just adjusted. And the important thing is this here. This is, we move a specific value to a specific memory location. So that's exactly what I had on the previous slide. And if pref and next are initialized as a counterfeit list entry, and if this code location is then triggered, it does exactly what we want to do. So it overrides the return address with a jump to our hooking address, and then we can, when this legitimate code is followed, the data-only attack is actually happening, and then we can install the hook during runtime. And this idea can be actually generalized in the sense that this move instruction is actually something like a write for as a data-oriented gadget. And you can then, if you search for this kind of gadgets, you can find similar instances. So you can find gadgets that do not implement ROP primitives, but that implement data-only primitives. The challenge is then to stitch those or this kind of gadgets together, but it turns out that you can also do arbitrary computations by just using those data-oriented gadgets. And we have an upcoming paper, well, it's only a submission, but eventually, hopefully public, where we demonstrate that this data-only attacks can be fully automated also for binaries. I think I skipped this one, but yesterday you saw the deserialization talk by Matthias. Unfortunately, I missed it, but that's actually something very similar to code reuse attack. So you inject data structure, in this case here just a fake value, and the deserialization is actually triggering a code reuse. And then as the last example of what I think is interesting is that the attacker can not only abuse specific code structures, but we also implemented a technique called counterfeit object-oriented programming, where the idea is that we abuse C++ objects. So we create fake objects. The objects are constructed in a specific way, and then we do not reuse small gadgets, but we perform full function code reuse. And it turns out that this kind of attack actually can bypass many of the available defenses. So all of the binary-only defenses that don't take C++ semantics into account can be bypassed. And in the paper we describe all the details, but it turns out that you can find the same thing like gadgets, but they are not just small gadgets that are just a few instructions, but you can find full functions that can be reused, and they can then serve as your building blocks of the attack. And the challenge is then to find this kind of main loop, and the main loop then allows you to call the different gadgets, You need to also stitch them together in a precise way. But this also works for C++, and we also have an implementation for Objective-C, where you can take as an input a binary, and it constructs this kind of exploit in an automated way for you. I need to skip this, but it's just explaining what we do. So we inject a fake object that's constructed in a specific way that helps us to do arbitrary computations again. So the conclusion, what I think is that we'll have a lot of more of this arms race in the future. So on the one hand, we see more and more attacks, especially data-oriented attacks will be challenging because it's hard to basically find them. If you, for example, remember the God mode exploit in Internet Explorer, I think 2 or 3 years ago, where only a single byte was overwritten by the attacker, and suddenly IE was running in higher privilege context. And if you take a look at many modern exploits, they do not leverage return-oriented programming or anymore, but they just have a few small primitives where they take information leaks, where they have a read or a write for, and then are able, via some kind of data-only attack, to bypass all of the existing defenses. Just as a last slide, a Twitter discussion you should probably follow. So I think 2 or 3 days ago, Halvar wrote a bit of a rumbling, and that very similar idea that he said Rob is dead. And he also says that Rob is basically only a small part, and the main challenge is the info leak and the read-write primitive, and especially if the attacker has some interpreter available to him, so in a browser context, or a JIT engine that's designed to generate code for the attacker, then it's pretty hard to basically prevent against. And I think he's right. As always, he's right. So he has many good points, and I think there we have many challenges to solve in the future. Thanks a lot.